Now let's see whether it is functionally correct or not. So the first input of the OR gate is S0 bar, S1 bar and I0, right? So we'll track that. So this is S0, this is S0, so this is S0 bar and this is S1 bar. So up till here you got S0 bar into S1 bar, it should be multiplied with I0, right? So the I0 is getting multiplied with this S0 bar and S1 bar. So this is the partial sum output 1. So this thing is P1. So next P2 will be S1 bar S0 into I1. S1 bar, this S1 bar into S0, this S0, this should be multiplied with I1, right? This is multiplying with input I1. So this is the partial sum 2. These two are getting ORed here. Similarly, partial sum 3 and 4 are available here. They are getting ORed, and then finally you are getting the OR of all the 4 partial sums. So our 4:1 multiplexer is correct. Functionally it is correct. Now let's design using conditional operator. We'll take one more project for this because I want to explain the difference between conditional operator and these logical equations. We'll see how the schematic will be different and how the implementation power and utilizations will be different for these two different ways of defining the multiplexer. So let's create new project, name it, what do we name? Data flow underscore 421 mux. Now I am using conditional operator CO. Next, create a file. I have named the file as mux underscore lo. So I am naming mux underscore co. Okay. Next. Same board we'll use, the jet board. Would you like to close? No. I want to see the outputs there and here, and then we'll compare. Okay. We'll give the same names of inputs and output combinations so that it is easy to compare. I'm copying this code as it is. See. Remember, you have given the name of mux underscore c, so your module name should also be mux underscore co. I'm changing it here. Now I'm commenting this line. I don't want to use the logic equation. I want to assign through conditional statement. So how does a conditional statement will look like? If you remember, it starts like this. It will ask for the MSB bit whether S1 is true or false. If it is true, then execute these line of statements in which if S0 is also true, if S1 is true and S0 true means that is 1 and 1, which is I3, and if S1 is true and S0 is false means that is 1 and 0, which is I2. Similarly, if S1 itself is false, then we will move to whether same thing, whether S0 is true or false. That means this is 0 and this is 1, which is I1, and if S1 is false and S0 is false, which is I0, right? Now this is a 4:1 multiplexer using a conditional operator. Look how the conditional operator we can do the next thing also. This is a single conditional operator which takes one input, which takes 3 inputs. As you can say, it is a ternary operator. It will question the first input and assign the expression that is available here to the output. So let's see the schematic of this multiplexer. Let's open elaborated design. Now see, it has not used any logic primitive gates, it has used the multiplexers instead, because the FPGA board has both logic primitives as well as these multiplexers. So in the conditional statement state, it has seen there is a multiplexer kind of operation. This is a multiplexer operation, so it has directly used the 2:1 multiplexers. So let's see the functionality. This is S0 is applying for a 2:1 multiplexer. It is decoding I0 and I1 in this 2:1 multiplexer, and in this 2:1 multiplexer it is decoding I2 and I3, and in final stage it is decoding one of these two outputs, right? So that is how we can build a 4:1 multiplexer using a 2:1 multiplex, 3:1 multiplexers. You can see this is a very good example how to design a 4:1 multiplexer using 2:1 multiplexers. So the advantage of using conditional operator is, now see how many nets it is taking. It is taking only 9 nets, right? You can count 1, 2, 3, 4, 5, 6, 7, 8 and 9. Only 9 nets it is taking, and the input output ports are 7 because we have defined 4 inputs and 2 control inputs and 1 output. So IO ports are 7 and 9 nets, and number of cells it is using is 3 cells. Now let's compare with our logic equation schematic. Here see how many cells it is taking. It is taking 11 cells. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 cells. And the IO ports are same because the same input combinations we have given. And it has taken 17 nets. As comparison with this, it has taken only 9 nets. There it has taken 17 nets. The more the nets, the complex will be your routing. And the complex will be your routing. The complex will be your design rules and all. And it will add more parasitics also. So we'll try to limit our design as simple as possible. So let's implement this and see what is the amount of utilizations that both of these designs are consuming. First of all, I'm implementing the multiplexer based design. So I'm not running the synthesis, I'm directly running the implementation step, because the implementation step will run the synthesis first. So here you can see there is no netlist available. Okay to launch synthesis first. Yes, automatically it will do synthesis as well as implementation. As it is doing the synthesis, we'll see the operation of this thing, how it is operating. See, S0 bar is connected to, S0 is connected to these two things, right? So what happens if S0 is 0, then I0 will be passed because default value is this. I0 will be passed here, and if S0 is 0, then from these two combinations I2 will be passed. Okay, I0 and I2 are readily available here, and then it is waiting for S1. If S1 is 0, then it will pass the I01, right? Because default is 0. So like this, it is passing I0 here based on the combination of S0 and S1. Similarly, if S0 is 1, then I1 will be passed. This path will be active, and I1 will be passed here. And if S0 is 1, that means from this path, what will be selected? I3 will be selected, right? So here I1 and I3 are available readily. Now based on the S1, if S1 is 1, then I1 will be passed, right? No, not I1. This is connected to I3. Yes, I3 will be passed. So 1, 1 means I3 will be passed. That is what we want also, right? I think synthesis is done. We'll see the synthesized design, open synthesized design, and implementation is also done. Let's open. Now see, this is the implemented design. And first of all, we'll see the reports of synthesis, report utilization. We'll name it utilization underscore. This is CO, right? Conditional operator. Now see, it has taken only one LUT to perform and 7 IO bonds or IO pads. And let's see the power that it is consuming. Name it underscore CO. So it is consuming almost 0.04 watts of logic power, which is almost 1%, and signal power is 0.020. Okay, remember these numbers. We'll compare this with the other design. The amount of power is on-chip power is 0.564. This is synthesized power, but let's see what is the implementation power. CO underscore implementation. The synthesized power and implementation are little bit different because the implementation power will taking into consideration of routing as well, but the synthesized power will take into the consideration of only logic gates or LUTs that it is using. Okay, so always take the implementation power because that is very close to your real power. So the synthesized implementation power is also same. You can see it is also consuming 80% and 20%. 80% is dynamic and 0.564. Now let's do the same thing for other design by using logic equation. We'll run the simulation. We'll run the implementation. I think synthesis is done. Yeah, it's still working. Yes, synthesis is done. Let's open the utilization of synthesis. Utilization underscore LO. See, it is also taking only one LUT, right? And 7 IOs, same as the conditional operator. Why? Because the JET board has many LUTs which are used to design the logic primitives. So all the logic primitives that are shown in the schematic are readily available in this LUT or designed using this LUT. You can say the LUT is a very powerful block that is available in FPGA. That LUT, that lookup table itself, designs all the logic primitives. So in the case of logic equation as well as in the case of conditional operation, you can see the amount of resource utilization is same, right? It is only taking one LUT here, and in this case also it is taking one LUT. So to visualize the difference between this logic operation based and conditional operation based, let's design a 32-bit inputs and 32-bit output multiplexer. What I meant is each input of the 4:1 multiplexer is now a 32-bit input as opposed to a single bit input here. So I am defining a 32-bit, is 31 down to 0, and 32-bit output. Okay, still it is a 4:1 multiplexer, but each input of the multiplexer is a 32-bit data. So I am saving the design. Again, we'll see the elaborated design for this. So remember, this is a logic operation based. So it should have gates, primitives instead of LUTs. Yes, it has gates, right? The functionality is almost similar, only change is the bus of inputs. Earlier it is a single bit data, now it is a 32-bit bus of data. In the case of output also. So the IO ports has increased from how many IOs earlier? 1, 2, 3, 4, 5, 6, 7 IOs. Now it is 162 IOs, and the cells are same, but the number of nets has changed to 483 nets. Similarly, we'll do the same thing in conditional operator also. We'll try to do the 32-bit data inputs and outputs. Saving this, and let's elaborate the design. Since it is a conditional operator, it should use the 2:1 multiplexers that are available in Vivado. So it is using the multiplexers. The only change is the buses, right? So see, the number of cells here are constant. Earlier it is 3, now it is also 3, but IO ports are changed to 162, same as here. The number of IO ports are 162. But see the number of nets that it is using. Here it is taking 226 nets, whereas here it is taking 483 nets, right? Now let's implement the design. First, we will implement the logic operation design. So I'm running the run implementation. Yes. Okay. Now after implementation, we'll see how many actual nets that it is consuming to design this circuit. So first it will do the synthesis, then it will go for implementation. See the process. Synthesis is going on. Remember, the RTL is taking 483 nets, but the synthesized nets and implemented nets might be different from the RTL nets. So implementation is done. Let's open the implemented schematic. So this is the implemented schematic. Now this is the actual schematic that is going to be implemented on your board. So it is using the actual LUT and the buffers that are available on the JET board, right? So now see the amount of nets. The amount of nets has decreased to only 107 nets. So we'll see the amount of utilization. Let's name it LO underscore synthesis of 32-bit. So it is still taking only one LUT. As you can see, only one LUT is sufficient to perform the 4:1 multiplexer operation, right? Now let's report the power of LO synthesis and 32-bit. So it is taking, when the design is ready, okay, it is taking almost 9.2 watts of power in synthesis, and we'll see how much power it is consuming in implementation as well. So this is the implemented power, which is 9.54 watts, right? It is taking almost 89% of dynamic power and 11% of device static power. So this is the implementation design, right? You can see the 107 nets are routed from here to here. It is using complete these two as input ports and this side as the output port, and it has routed through the LUT, right? Only one LUT is sufficient. That LUT is sitting here. This is the LUT that it has implemented, and you can see the routing of these 107 nets. The same thing we'll do for conditional operator also, and we'll see how much utilization it is having. So remember these terms, these numbers. In the logic operation case, we have consumed 9.54 watts of power. Now let's do the implementation of conditional operator case. So I'm running the implementation. Yes. Okay. Let's see the internal structures of these things. I mean, some more reports we'll see. Report utilization of the implementation. This is a LO, right? LO based design of 32-bit. So you can see it is using one of the slice from 53,000 slice LUTs that is available in JetBoard, and one of the logic LUT it is taking, and the number of IOs are 69. We are not doing any timing reports because we have not given any timing constraints. If you give any timing constraint, then you can see the amount of setup, hold, and slacks of these things. We will discuss these things when we discuss the static timing analysis. Okay, right now we are only focusing on resource utilization as well as the power consumption of the design. Okay, let's hope this is done. Yes, synthesis is done for the conditional operation base. So let's elaborate the synthesized design. So now let's see, the amount of nets has increased from 200 something to 300 nets. But in the case of logic operation, the amount of nets are very low, which is 107 nets, right? For both synthesis and implementation. Let's see the implemented design of this conditional operation base. So how many nets it is consuming? It is consuming total 227 nets, but after implementation, it has gone up to 324 nets. Now you see the difference between these two designs. This design is very compact, which is only taking 107 nets, right? And it has routed from here to here. But in the case of conditional operator, it has used 324 nets and it has routed from here to here, which is very complex as well as which will take lot of delay also, right? So the conditional operation based design will be helpful if your design is very small, but once you go for larger designs, you can see the number of nets are increased in conditional operator based design compared to the logical operation based design. Similarly, we will report the power of conditional operation based design. Let's report the power. This is CO based design, implemented power of 32-bit design. Now let's see how much amount of power it is consuming. See, it is consuming 16.22 watts of power. The increase in power is because of the number of nets it is taking. As you increase the number of nets, it will add lot of resistance and capacitance and inductance parasitics to these nets, and it will consume more amount of power. So in the case of logic based operation, the amount of power is only 9.54 watts, but in this case, the amount of power is 16 watts. So you have seen the two different designs of multiplexer and you have compared the designs using implemented power as well as the implemented resources, right? So this is how you can optimize the design whichever way you want. If you have a smaller design, you go with conditional operator. If you have larger design, you go with logic operations, right? Now let's create a new project for 4:1 4-bit full adder. Now I'll create a new project to show you how to build a 4-bit adder by using data flow modeling. We have already built a 4-bit adder by using a 4 full adders in gate level modeling. Right now we will do using data flow modeling. Adder 4-bit in data flow. Data flow full adder. I'm creating a file. Next, next, I'll select the Z Next, finish. You want to close. Yes. Now let's start writing the code for the 4-bit full adder using data flow. As uh, in previous examples, we have seen how to write the 4-bit full adder using gate level primitives, right? In the gate level modeling. Now we'll see using data flow modeling. This is the full adder. I want sum and carry out, C out, comma sum, and I have three inputs A, comma B, comma C in. So I am defining them. Output C out is a single bit output. Output output sum is a 3-bit output, 4-bit output. Let's take 4-bit full adder. And my inputs A and B are 4-bit inputs. Down to 0, A comma B, and my Cin is a single bit input. Right? So what I want is I want carry out and sum should be assigned to the sum of A, B, and Cn. So I can do it with single line of code like this. I am using the concatenation operator. C out comma sum is equals to my A plus B plus Cn. That's it. This will do the addition of these three and put the output in C out and sum. So let's save this and we'll see the schematic of this elaborated design. Now let's see, it is using the RTL adder that is available inside the Verilog. Instead of using primitives, it has used two RTL adders and then it has provided the 4-bit output of sum and 1-bit input, 1-bit output of carryout. So if you want to check the functionality of this, you can run the simulation. And right now I'm not using any test bench. In the previous gate delay models also, or logical and reduction operator models also, we have not used any test bench. We have directly forced the constant. Similarly, we will force the constants here. Let's say my A is a 4-bit data of 4. And my B is say 7. My C in is 1. And let's run this for 10 nanoseconds. We'll convert this into binary or directly decimal. So 4 plus 7 is 11 and with carry it will be 12. So the sum is 12 and there is no carry out. To get the carry out, what you need to do, you have to add F and F. So I am force constant. I am giving my A as F and B also as F. So let's see the output. See, my sum is also 15 with carry 1, right? So our full adder is working perfectly fine. You can do the implementation of this full adder also and you can check the output in Jetboard, right? So this is with this example, I will conclude the data flow modeling. In the coming session, I will teach you the behavioral modeling. In the behavioral modeling, we will see different blocks like initial block, always blocks, which are very essential. So let's stop this session here.